Hello Math 152 students. In this video we'll take a look at some content in 10.3. 10.3 is going to feel very similar to 10.2. The biggest difference is the parameter that we're looking at. In 10.2 the parameter was the population proportion. We were trying to make a claim about what happened to the population proportion and test that using collected data. In 10.3 we will be making a claim about a population mean, looking at averages, and test that hypothesis based on data that we've collected. The steps are going to be very, very similar. The difference will be in our conditions, symbols, and then the type of test we actually run when we get to StatCrunch. So our step one is still to determine the null and alternative hypotheses. You still have the option for two-tailed, left-tailed, or right-tailed. You just want to notice that instead of using p, we are now using mu for population mean. Then, step two, make sure you've specified your level of significance, that alpha. And typically the problem will tell you either 0.05, 0.01, or 0.1. But if not, you need to pick an appropriate level depending on the seriousness of making your type 1 error. So remember that our most common level of significance is 0.05, 5%, but we do see those other two as well. Step 3 is going to be to find our test statistic and p-value. We will use StatCrunch to do this, very similar to 10.2, and we will focus on the p-value and interpreting that. Step 4 is to make your decision. Keep in mind, the way we interpret the p-value is identical. Doesn't matter if we're looking at proportions or means. If your p-value is less than your alpha, you reject your null hypothesis, meaning we say that's not true. And then if we reject the null, we accept the alternative. Sometimes we will say this as we have evidence to support the alternative hypothesis. Now, what happens if your p-value is greater than alpha? If your p-value is greater than alpha, you can't reject the null. Or you could say something like, I can't rule out that the null is true, and I can't support the alternative. So we'll see both of those scenarios today. But this idea, if p is less than alpha, reject the null and accept the alternative, is what you want to remember for the entire chapter. It's the same thing we'll see in chapter 11 as well. So step 5, don't forget about stating your conclusion in everyday language. You want to not use the formal language of rejecting or supporting. You want to go back in the context of the problem and sort of restate the researcher's claim or your claim and whether it's supported or not. So the next thing before we jump into an example is to go back over our conditions we need to check. The conditions we need to check for hypothesis testing for means mimic what we saw in chapters 8 and 9 for means. You need to either have a large data set, we're going to classify that as greater than 30 pieces of data, a sample size of 30 or more, we could say, or you could have less than 30 and know that your underlying population is normal, or if you have less than 30 and they don't tell you anything about your underlying population, you would need to check the box plot and QQ plots for your sample. So this is exactly what we had to do before we constructed a confidence interval. And a lot of times you will be in either the first or really the third. Occasionally they'll give you less than 30 and tell you the population, the underlying population is normal. But the first and third are a little more typical. So let's go ahead and jump into an example from your book. We're going to go to page 458 and start with number 23, and then we'll contrast with number 24. So let me back up here to 23. And I picked this one partially because they give us a context that's maybe a little bit less familiar. Here, they tell us calcium is essential to tree growth, and in 1990, the concentration of calcium in precipitation in a particular location was 0.11 milligrams per milliliter. Then we have a random sample of 10 precipitation dates, and it looks like the calcium in those precipitation samples for 2014, and we have them displayed here. So notice a couple of things. This 1990 and 0.11 is a prior value. Our data was collected in 2014, let's see, 24 years later, and notice that the values, we don't have any that are 0.11, but remember this is an average for 1990, but it's not really clear what's going on. Some of them are pretty close, some of them are a bit above, and notice this one is a bit below. So let's read on. They tell us that a normal probability plot suggests the data could have come from a population that is normally distributed. A box plot does not show any outliers. Basically, what they're telling us here is that our conditions check. I actually want us to verify that as well, because most of the time they won't tell you this and they'll just skip to your next sentence. Does the sample evidence suggest that calcium concentrations have changed since 1990? Use the alpha equals 0.05 level of significance. So a couple of points here. Notice there's nothing in here, nothing in our setup that gave us proportions or was really dealing with percents. We were thinking about average calcium levels, and these numbers we could find an average for, but they don't really lend themselves to proportions. So our setup is going to feel different. Then in our wording, notice that we're not making a claim that the concentrations have increased or decreased. We're just asking, does it support the claim that concentrations have changed? So let's go ahead and look back at our slide. This is going to be a two-tailed test, and I actually forgot to modify this a little bit. I had done some copying and pasting. So make sure we note that. It's a two-tailed test where our null hypothesis, if nothing has changed, the mean concentration of the calcium is still 0.11. We don't need to include units here. And our alternative is that it's changed, it's no longer that value, so our not equal one. Step 2, we've got our level of significance is 0.05. And we need to check our conditions, even though they told us they checked, and then go to StatCrunch and find our p-value. So let's go ahead and click over. Notice for this problem, you didn't see the SC beside 23, so you would need to type this data into a blank StatCrunch page, like I've done here. And then you have two options. You could create your QQ plot and your box plot separately. You also have the option to do that in one step in StatCrunch. So let me show you that option, and it will give us the p-value at the same time. So go to your stat, and the procedure that we'll use for mean is called the t-stats. Your book talks a lot about the t-distribution and what that is. You want to do a little bit of the background reading in 10.3 on the t-distribution, but we're not going to be using the by hand tables and really doing a lot by hand with this t-distribution. The t-distribution is similar to the normal, but it's more flexible. It allows you to account for a little bit of skew and adjust things a little bit more. We are dealing with one sample. We have one column of data, the data option. Our calcium concentrations are in column 1, no grouping, and you want to make sure you change the value for your mu naught or the population mean in your null hypothesis. We do have the two-tailed tests, so we're good to go there. And then for the optional graphs and tables, your option here to select a box plot and a QQ plot will go ahead and allow us to look at those conditions and check those at the same time. So make sure both of those are selected, and let's hit compute. Okay, so notice they tell you a couple of things: the sample mean, the standard error, which is the standard deviation for our sample, where we're incorporating the 10 So kind of going back to those formulas, similar to what we saw in chapters 8 and 9, but in this case it's using the t-distribution, so it's not exactly the computations we saw in chapter 8. Then they tell you the t-statistic. So the t-statistic is our test statistic, similar to a z-score. You want to think about interpreting this just like you would interpret a z-score. Here, this is saying our sample mean is about 1.7 standard deviations above what we would expect if the null is true. In other words, that's pretty far above the 0.11 that we were expecting to see if we still had a concentration of 0.11. Then the p-value is 0.122. The p-value is telling us the probability of observing a sample mean of 0.1568. That's the average of these. The probability of that happening is about 12% if we assume the actual mean is 0.11. So what does this mean? This is telling us, well, it's not a large probability that we would see about 0.16 as our concentration if we were expecting 0.11. It's not a large probability that that would happen, but it tells us that it's not unusual. In other words, it wouldn't be unusual to see data that results in this type of sample mean if we still have a concentration on average of 0.11. So let's go ahead and go back to our slide, put in that p-value, and make our decision. Most of the time when I'm working with hypothesis testing, I only include my p-value here. Sometimes your MyMathLab will ask you for your test statistic to put that in. And remember, your test statistic is the t-stat that's telling you, and you can interpret as these standard deviations above the mean when you're comparing your sample mean to the mean in your null hypothesis. Okay, so step 4, compare this 0.122 to our alpha. Our alpha is 0.05, so this is not smaller than our alpha. This is larger than our alpha. So remember, just going back to our previous slide, if your p-value is smaller than alpha, you reject the null and accept the alternative. If your p-value is larger than alpha, we can't reject the null. So I'll just type that out. Our p-value is larger than alpha. Just put the 0.05 in there. So we can't reject the null. In other words, we don't have enough evidence to reject the null and support the alternative. So what we could say is we can't rule out that the actual mean is still 0.11, or we could also say we don't have enough evidence to support the alternative. So I'm going to write it like that. We don't have enough evidence to say that the calcium concentration has increased. Or I should say, in this case, have changed. Sorry about that. So we were doing a two-tailed test. Our alternative did not specify an increase or a decrease, so we don't have enough evidence to say that the calcium levels have changed. So in this case, in a practical setting, if you as the researcher really think that 24 years later, after we had this average of 0.11, something has changed, what are your options now? This test was sort of inconclusive. You don't know that the actual concentration is still 0.11. In fact, when we looked at our mean, it was a bit higher, but there's not enough evidence to support that it's changed, partly because we only have 10 data values. All right, guys, this recording is about to end, so we'll pick up with wrapping up this example and our next one in the next video.